everyone, and welcome to another video. So we made it. It is the last week of our AE501 class, so let's jump right over to the lecture and see how we're going to end this class. Actually, I'm really glad we're actually ending on this topic because this topic is my absolute favorite of the entire class, and that is the topic of optimization. In fact, you remember from last week in week 9, we actually got a jump start and started talking a little bit about optimization, just talking about what it is, the big ideas, and then we're going to start digging into some of the actual algorithms and some of the nitty-gritty. So again, optimization, it should be an entire class. It should be an entire year of study, in fact. It should be an entire master's degree. In fact, come to think of it, it should be almost like an entire lifetime of study for optimization. I had a professor one time that said pretty much any engineering problem can be posed as an optimization problem. And I almost want to take that one step further. I feel like anything in life is an optimization problem because really what optimization is all about is trying to do the best you can with what you're given, right? And that's the story of life in general. So it's really exciting that we're going to be able to talk about some of the mathematical underpinnings and foundations and ideas around that really big idea. So, with that being said, like I said, last week we started talking about optimization at a somewhat high level. This Taylor series we saw was a little bit of a mathematical, sterile topic, but we're going to see this week how does that play into things like unconstrained optimization. So we're going to start off this week talking about unconstrained optimization. That's where you have a cost or a utility function and you're just trying to minimize or maximize that function without any constraints on what the solution can be. Okay, so unconstrained optimization is a very popular topic. There's a lot of power behind it. It's applicable to a lot of different fields, but it is, let's pay attention to this adjective in front where it says unconstrained. So that's a different class of problem than, say, a constrained problem, which we will look at later. But like I said, really, we should have spent the entire class on this topic to really have a chance of scratching the surface. What we're going to talk about here in this last week is really just some big ideas. So again, unconstrained optimization is right here. Let's just talk about the big idea, okay? Then I want to start looking at some numerical algorithms of how can you write an algorithm to solve some of these unconstrained optimization problems. And probably the most famous algorithm that you're going to see is known as the gradient descent method. So gradient descent, we're going to examine it again in a pretty sterile framework right here with a kind of a toy academic application and problem. But gradient descent shows up all over the place. It shows up in things like system optimization. It shows up in AI and ML. So for example, training neural networks or training a lot of these AI algorithms really boil down at the end of the day to applying the gradient descent algorithm on large systems. So let's look at it in a very small, simple situation right here. But keep in mind that this idea can be scaled up to huge, huge systems, and it's incredibly powerful, okay? So this is the idea of what is the gradient descent algorithm. And we're going to see that really a lot of these numerical optimization algorithms have two parts to it. One is you need to choose what's known as a descent direction or a direction in which you want to take a step. So that's one way you can do this is using the gradient descent method. That is used to pick a direction. The next thing that you have to put into your numerical algorithm is a step size. So once you know which direction you're going to go, how far are you going to step in that direction? So I'd like to look at one of probably the easiest ways to choose a step size is the constant or diminishing step size algorithm. So again, this is a quick little 27-minute discussion talking about what this technique is. Then I want to get a little bit fancier, okay? There's other ways you can choose a step size. So the line minimization algorithm or solution or technique is a much more sophisticated, albeit a little bit more complicated way to solve this problem. And that's just another way that you can pick a step size, okay? And then third, I would like to look at, this is actually used quite extensively on a lot of commercial optimization packages or in industry. This is what's known as the Armijo rule. And again, at the end of the day, all this is, it's another way to solve or to pick a step size. So gradient descent or some other method is going to get you a direction, and then you pick one of these three, or in fact, there's plenty more techniques of how to choose a step size, but at the end of the day, that's what these three videos are talking about, is just three different ways to pick a step size. Now, let me talk about this new Armijo rule discussion here. You'll notice here that this is it's an hour and 17-minute long lecture. Really, for the homework, though, all you need is the first 12 minutes. So feel free to watch the entire video if you're interested, but really, you're going to see that this boils down to basically a very small algorithm, and we can detail that in the first 12 minutes. So again, if you are interested, feel free to check out the whole thing, but you're only going to need to watch the first 12 minutes to tackle the homework. Okay. Yeah, and then the last thing I want to talk about, like we said earlier, a lot of this discussion here is going to be in the unconstrained optimization category, where you don't have constraints. But a large number of optimization problems, and like I said, a large number of engineering, science, and life problems in general, we obviously have constraints, right? We can't do anything we want. We have things like, oh, your structure has to weigh less than a certain amount. It can't cost more than X, et cetera, et cetera. So unconstrained optimization will only get you so far. Eventually, you're going to have to start looking at constrained optimization problems where you need to choose solutions that obey a certain set of rules or constraints. So we're only going to have time to look at probably one of the most famous families of these constrained optimization problems, and that's what's known as a linear program. So this is basically where you have linear cost functions and you have linear constraints. And if that's the case, you have what's known as a linear program, and in this hour-long discussion, we'll introduce that topic, and we will take a look at how to formulate some problems as linear programs. And again, like I said, this is barely scratching the surface. There is an entire discipline looking at different types of constrained optimization problems. I just want to introduce this idea here, and then maybe later on in the MAE program, we'll get a chance to look at other types of constrained optimization problems. So that's the game plan for our lecture discussion and topics this week. Like I said, it's very exciting. This is the last week of the class, and I'm glad we're ending on a high note. And again, this is probably going to be some of the most exciting things we're going to be able to talk about all quarter. So, with that being said, let's jump over to the homework and see how we're going to apply this. Alright, so here we are. Here's homework 10. So the first problem is just looking at a Taylor series and, I guess, a Maclaurin series, but we're going to see that a Maclaurin series is really just a special case of a Taylor series. But anyway, I'd like to consider a function, really simple, a sine function. Okay? And I'd like to look at computing the Maclaurin series of this function. And again, we're going to see that in the video, I think if you've already watched it, you'll see that a Maclaurin series is really just a Taylor series at x equals 0. Okay? And then let's also look at how about a Taylor series expansion of this function, but instead of it being at x equals 0, let's look at expanding this around a point x is equal to pi over 3. Okay? And then for part C, I'd like you to go ahead and plot partial sums of these Maclaurin and Taylor series approximations and just change how many terms you take in the sum. So again, you're going to see that in the Taylor series discussion, it's just like a Fourier series in the sense that this is a way to approximate a function by taking an infinite number of terms and summations. But we don't want to take infinite numbers. Let's just see what happens if you take, like, I don't know, 5 terms and ignore all the other higher order terms. Do you have a reasonable approximation of your function or not? So that's all part C is looking at, is just plot your different levels of fidelity of partial sums and compare it to the original function up here and see what it looks like, right? Okay, and then part D and E are actually, there's actually a couple ways you can skin this cat. So all I'd like to do now is, okay, in parts A, B, and C, we looked at Taylor series of a function sine of x. Well, can you use your results from the previous parts to compute the Maclaurin or the Taylor series of cosine of x? And again, maybe the hint to remember is, well, cosine is just the derivative of sine. So instead of going back and brute forcing and doing steps A, B, and C again for cosine of x, can you use what you already did for part A and just quickly get the Maclaurin series for cosine of x, okay? And then same thing for part E. I'll let you read this, but it's pretty much the same idea, right? Now let's make up another function, which is x times cosine of x. And again, see if you can use previous results to quickly compute the Maclaurin series of g of x, okay? All right, so that's problem 1. Again, sterile mathematical problem. It doesn't have a whole ton to do with optimization yet, but let's now look at problem 2, where we will definitely get into optimization. So for problem 2, we are going to look at applying the line search combined with a gradient descent method to go ahead and try to minimize this cost function right here. So I'm going to cook up some cost function. You can see it's a function of two independent variables or decision variables, an x1 and an x2, and it looks like this. I don't know. In fact, maybe the easiest thing that you might want to do is go ahead and plot what this thing looks like, just so you can have a rough idea of what this surface looks like, right? And then what I'd like to ask is, in this problem, what we're going to be doing is we're just going to do one step of the numerical optimization process. So I'm going to give you a starting point right here. So let's pretend that your numerical optimization scheme, you guess and you say, this is where I think the minimum of this function is. And now we're going to use gradient descent to see if we can find a direction in order to make our guess better, right? So you're going to go ahead and compute the descent direction and you normalize it. This is a key part of it, right? Make sure when you choose a descent direction, you normalize it so it's a unit vector in part A, okay? So once you have that direction in place, you now know which direction are you going to walk. Part B is saying, all right, now pick the step size, alpha k, of how far are you going to walk in this direction dk. And the way you're going to pick this is by using the line minimization technique. So again, I think the easiest thing to do is obviously watch this video where I pretty much do an exact, a very similar operation and example of how to do this. So as soon as you watch this video, I think this is going to make a lot of sense right here, okay? So you can do part A and part B, and basically what that's going to let you do is compute the next step, right? We're saying you start here at x of k. I'm going to now walk in the direction dk by the amount alpha k, and that's going to get me to the point x of k plus 1, okay? Now, the whole idea, right, is we are hoping that the function value at their new location, x of k plus 1, is less than the function value at where you're standing at right now. So all I want you to do in part C is just show me that this is true, that the cost has actually gone down, and we've done some productive work with this algorithm. That's all we're doing, right? And then I guess in part D, yeah, it might be interesting to do a three-dimensional plot of the entire surface of the cost function. So plot this entire thing using plot 3D, and then plot the location of the f of xk, and plot f of xk plus 1. So I just want to see where are all these artifacts and things that we're computing, how do they all tie into one picture? And again, hopefully once you do this picture, a lot of this is going to make sense. Okay, so problem 2 is you're just taking a single step with these parameters, okay? Now, let's go over here to problem 3. So problem 3, let's do a full-on numerical unconstrained optimization. So instead of taking one step, we're going to be taking multiple steps, okay? So let's consider the exact same function that we were dealing with in problem 2, okay? And like I said, we are going to now do an entire optimization, a numerical optimization algorithm and routine to basically start at some guessed starting point and see if this algorithm can find a minimum of the cost function, right? Okay, so for part A, you're going to have to create a MATLAB function, which its only job in life is you tell me an x1 and an x2, it basically computes this. It just computes the function value at a given point x, okay? So in goes x, out comes f of x, or the cost, okay? Similarly, in part B, you should be able to compute the gradient of f of x. So make yourself a MATLAB function where, same thing, in goes x, but out comes gradient of x, okay? And then we can use those results, both part A and part B. So in part C, actually I guess you technically only need part B, and technically you actually only need the analytical gradient is what I'm asking for right here. Once you compute the analytical gradient, you should be able to get the stationary points of this cost function. So part C does not need your MATLAB function, right? You can do this all on pen and paper by just looking at the analytical gradient of f and then computing the stationary points, okay? Okay, then for the next part, what I would like to do is, yeah, let's make a plot of this entire thing and show the surface and show these stationary points that you just computed from part C. Again, this is just going to help with the visualization, all right? Now, we know that these stationary points are special about special points on the domain of the cost function because local minima and local maxima are going to live there, right? And the way we're going to decide which one of these are, is it a minima, is it a maxima, is it a saddle point, etc., is by looking at the Hessian. Okay, and again, if you watch the videos, we talk about what the Hessian is and how to interpret it. So I think once you watch that video and see the Hessian portion, Part E is going to make sense. Part E is going to allow you to say something about what these stationary points in Part C are. What are they doing, right? Okay, once we've done all this analysis, parts A, B, C, D, and E, that's, just getting familiar with the problem, figuring out what should happen with our algorithm, let's go ahead and do the algorithm now, okay? So I'm just going to give you some parameters for the algorithm. I'm going to say, start at this location, and we are basically going to keep using the the gradient descent plus the Armijo rule step size calculation to just let this thing rip. We're gonna take multiple steps, and we're going to terminate this algorithm when certain conditions are met, namely when the norm of the gradient is less than 0.001, meaning that you've come pretty close to a stationary point, right? Okay, and then I've given you some parameters to use for the Armijo rule, and again, if you watch the first 12 minutes of that Armijo rule lecture, all these numbers are going to make sense of where these get plugged in. Okay, and again, I think it'd be helpful if you plot the progression of the algorithm. So I'd like to see when you start here at x0, where's the point x1? Or x2, or x3, or x4, or x5, or however many x's it takes until you reach a location where this is true, where this norm of the gradient is less than 0, and then you're going to terminate. So what you should have is you should have a plot of the surface, and then a plot of a whole bunch of points either on the surface or down there in the domain of the function, just showing where does the algorithm go as it's progressing, okay? And then for part G, what I'd like to consider, and I don't want to give too much away about this, is, okay, pick a new starting location. Okay, instead of minus 0.5 and 1.75, how about minus 0.6 and 1.75? So I perturb it by just a tiny little bit in the x1 dimension. And what happens? All right, so I'll leave it at that. Yeah, problem 3 is a lot of fun, but you are going to have to code this thing up in MATLAB. So let me know early if you run into any issues, because it's one of these things where I'm sure you can make these really silly little programming errors which could screw up your algorithm, but hopefully we'll all get through this. So again, maybe the only advice is don't postpone or procrastinate on problem 3. Get going early so that myself or the TA can provide some help. Okay, and then the last problem of the class is problem 4. So linear programming. What if we have constraints? So again, the idea is, okay, let's say you've got a cost function, right? I guess technically I should highlight only the cost function, right? Here's the cost function, okay? And you notice it's linear, okay? It's linear in x1, x2, x3, okay? So I want to now minimize this over x. And x here is R3, okay? So if all you had was this part, this is an unconstrained optimization problem because we're saying x can be anything. It can be anything in R3. It can be any point in three-dimensional space, okay? But now, let's add on these constraints down here. So really, if you read this, this is actually 4 constraints. Here's a constraint, and then x1 has got to be greater than or equal to 0. That's constraint number 2. x2 has got to be greater than or equal to 0. That's constraint number 3. And finally, x3 has to be greater than or equal to 0. That's constraint number 4. But all of these constraints are also linear, right? So you have a linear cost function followed by linear constraints. So you've got a linear program on your hands. So the first thing I want to do is get a handle on what does the feasible set look like, okay? And again, if you watch the video on linear program, I'll talk about what is a feasible set, how do we get this set up. If you think about this long enough, right, we're taking all of R3, right, all of three-dimensional space, and we are imposing 4 constraints on this. So that is going to chop off certain areas of the R3 space, and those are not going to be admissible anymore. So all I want to look at is what parts of R3 are legal or admissible, okay? We're going to see that what this should look like is you should have, it's not going to be a smooth shape or anything like that. it's going to be kind of what's referred to as a polytope. It's going to be something where there are sharp edges or faces all over this thing, okay? And what I'd like you to do in part B is just look at where are the extreme points, or you can almost think of them as like vertices of this polytope. Where are those, okay? And then in part C, what you can do is, one way to skin this cat is we could go ahead and evaluate the cost function at all of these extreme points that you find in part B. So there's not going to be a ton, right? I think it's going to be, I don't know, less than 10. So you could brute force this thing and actually just go ahead and try to find out what is the cost function at all of these different extreme points. The other thing you could also do is I'd like you to examine a couple of other random points inside the feasible set. So pick somewhere that is not an extreme point and just find some random spot in the feasible set and evaluate the cost function. So really what we're doing in part C is this is sort of like a brute force shotgun spray and pray method of trying to find the optimal solution. We're just going to pick a whole ton of locations all over the place and see which one of them get you the minimum cost function value, okay? Okay, so that's what we're going to do here. We're going to spray and pray. And then in part D, MATLAB actually has a function called linprog, which is designed for solving linear programs. So I'd like everyone to just read the documentation on linprog, figure out how to take our problem right here and jam it into arguments that you can pass to linprog, and MATLAB will go ahead and solve this linear program for you. So, yeah, that's pretty much it. I guess it's a little anticlimactic that we're ending on this note. Yeah, I don't have too much else to say, but other than I had a great time in AE501 with everyone. I hope everyone had a good experience with the class. This is probably a great spot to leave it at this point, and let me know if you've got questions over email, and I hope I'll catch some people at office hours. But otherwise, yeah, it was a great time with everyone, and I look forward to seeing people in a future class. All right, I'll talk to everyone later. Bye.